right? I'm hanging the disc from the ceiling. Let's say that it is, in fact, a disc. And for the time being, let's say it has a moment of inertia I, but we will eventually substitute in 1/2 mr squared. Let's say the disk has a mass of 3m. I'm using a lowercase m here on purpose and a capital M here on purpose. I want you to realize this is the generic formula for the moment of inertia of a disk. You have it already in your notes, disc, ring, ball, stuff like that. I'm just reprinting it here. And we're going to say that it has a radius of curvature of r. Okay? Again, big R here is just a placeholder saying that the moment of inertia of any disk is 1/2 times the disk's mass times the disk's radius squared. I'm saying that our actual disk has a mass of 3 times capital M and has a radius of lowercase r. I'm also going to say that the box we're hanging has mass capital M, 1 times that. Now, if I was to ask you how fast is the disk spinning when this block descends a distance h, that's a problem you should be able to do because we've talked about this problem a bit. Now, we'll come back to this question, but we would start by saying the box has gravitational potential energy when it's here, and when the box descends down to here, it has kinetic energy, and the disk has kinetic energy. We've done conservation of energy problems. Not this one, but we've done conservation of energy problems. I'd like to do a different problem today. I want to do a problem where we use Newton's second law for this. That's going to be a little different than what we've done so far, but that's really where I want to go. It's the last thing we have to talk about when it comes to rotational motion, and then we'll need to do some practice. Newton's second law for torque is the same as Newton's second law for force. I already highlighted that in class once, but I want to remind you, Newton's second law for force is net force equals ma. Newton's second law for torque is net torque equals I alpha. Solving a Newton's second law problem in this fashion is exactly the same as problems we've already done. This is an Atwood machine. In the same way that the car on the table and the weight hanging off the table was an Atwood machine. Remember that lab we did first semester? This is the same thing. The car on the table represented inertia that was on the table, and the weight that was hung off the table represented the inertia that was hung off the table. In this problem, which we just saw in front of us, the disk represents rotational inertia, while the mass represents linear inertia. But they both are going to have their role here. We've done Newton's law problems before. So part of this problem deals with the mass that is hung. And we've done this problem already, so I don't want to spend a lot of time on trying to convince you how to do it. There's a downward force, mg. There's an upwards force, tension. That's it. Those are the two forces that act on the mass. They are unbalanced. Not a surprise. I expected it's going to accelerate downwards. In fact, I'm going to make downwards the positive direction. And I'll go over here and do the problem we've done before. mg minus tension equals ma. And note that that's as far as we can go. Right? We don't have any other information about what's going on. This tells us what's happening to the mass. If we want to figure more out, we're going to have to deal with the pulley. The pulley has inertia. So to deal with the pulley, it's different because there's torque acting on the pulley. So we have to do net torque, which we've done before. We did it for statics. It's the same thing. we have to find all of the torques acting on the pulley. Now, just so you know, there are 3 forces acting on the pulley. You may not know what they are, but there are 3. If you can work them out, good for you. You should. If you can't, then you should probably pay close attention, because there is downwards tension acting on the pulley. The pulley has weight, 3 mg. The pulley has some kind of normal force or something acting upwards to hold it in place. Those are the 3 forces acting on the pulley. Now, truth be told, these 3 forces don't all cause a torque. A torque requires a torque arm, a force, and consideration of the angle between those 2 things. 2 of these forces don't cause a torque because they have no torque arm. The normal force causes no torque. It acts at the center of mass, no torque arm. The weight causes no torque. It acts at the center of mass, therefore no torque arm. The only thing that actually causes a torque is the tension. It acts at the edge of the disc, so it causes a torque. So let's talk about how to calculate that torque. The torque from the tension will be R, the radius of the disc, times T, the size of the tension acting on the edge of the disc, times the sine of 90 degrees. Because when I look at this picture, if this is R, they clearly are at a right angle to each other. Now, in your notes, this might just be a nice little aside. Whenever you have a pulley, strings always come off tangent. So they always apply maximum torque. Any pulley that's circular is going to have a sine of 90 degrees for the angle. That's why pulleys work the way they do. The string always comes off at a tangent, and therefore it's always perpendicular to the radius. Always. You don't even have to think about it. So, one difference in Newton's second law for torques is that you have to evaluate the torque. We won't just list them like we do forces. We have to evaluate them. Where do they act on the object? All right, once you got that, we can start Newton's second law, which says add up all the torques, set it equal to I alpha. So we have one torque, R times T. I'm going to set that equal to I alpha. Now, when we've done these problems in the past, if you remember, we usually got things that we could line up that would be the same. And we'd cancel one out and solve for the other one. That's how we did them before. So we want to try and do that again. So there's a couple steps here. Step number 1, we want to ask if this is true. We want to ask that question. Meaning, is the motion of the pulley connected to the motion of the block? Does a rotation of the pulley result in the block moving a circumference? I'm telling you that question because you need to ask that question at this moment. If the answer is yes, then this is true. It's important that you ask the question because it means we can put everything in terms of one of the accelerations. Yes, sir. How do I know these are equal, or where did this equation come from? Which one of those questions are you asking?
I'm saying like how do you
Again, are you asking like, where did this equation come from?
Yeah.
Okay, it comes from the whole group of them when we were dealing with kinematics. when we were trying to compare rotational motion and linear motion. So this is the relationship that relates acceleration to angular acceleration, but it's only true if your object's rotation is linked up to how far something is moving. Like in this case, this string, if I wrap one wrap around the outside of that pulley, when it unwraps this way, the weight clearly goes down one full circumference because the string wraps all the way around the outside of the pulley. If that's true, then this relationship is true. It's the same condition we use for rolling. When something is rolling, we say that this condition is true. One rotation of the wheel will result in the object moving one circumference. Okay? All right, so with that being true, we can go back over here and write this as RT equals I A over R. Now, truthfully, right now, we could probably get a solution, but it would have I in it. It's not a problem, but that's what we would do. We'd probably do something like this. I'd probably say, well, you could solve this for T. If I solve that for T, I could do substitution. This would give me a way of finding out what the acceleration is. It would have things in it that I think are reasonable. You know, how big the pulley is and what kind of inertia it has. So let's try that. Let's see if we can get a relationship for the acceleration. I want you to see something. So I'm going to shift this off to the side so I have a little more room. And I'll get mg minus I over r squared A equals ma. I want to find the acceleration. So mg equals I over r squared A plus ma. I'm going to factor out the a's. mg equals I over r squared plus m times a. Now, this is where I want to really stop you and make you think for a minute. This is the unbalanced force. We hung a weight off the pulley. This is inertia. It combines both inertias. And this is how fast the system accelerates. You saw it happen in front of you, right? If I make I bigger, A had to get smaller because I had the same weight hanging off the edge. Do you see that? So I move the masses to the edge. The inertia got bigger. So everything in the parentheses here got bigger. That meant the acceleration had to get smaller. This is one of those things when you're asked, does your relationship agree with your prediction? We said in class, yeah, you put the things on the outside, it's harder to turn, so it'll accelerate less. Here's the math that shows that that's true. If I is harder to turn, everything in the parentheses here becomes a bigger number. But does the weight you've hung change? No. So if everything that on this side has to get bigger, the acceleration has to get smaller. This math supports our hypothesis. Now, here's something more important. Oftentimes, you're given information about the shape of your object. In this case, we were given information about the shape. We were told the moment of inertia was that of a disk. I'm putting in 1/2 times the mass of the disk, which was 3m, times r squared. Right, that is the moment of inertia of a disk, but I put in the mass of the actual disk because it was 3m. I'm using this as an example because you need to see this kind of stuff. I can put in the moment of inertia. Truthfully, it would have been easier to put it in earlier, but I wanted you to see all of the parts. So I put this in. Do you see that the R's cancel out? That is super common because how fast the weight falls depends on how big R is. So the R's cancel and I get 3/2 M plus M all times A. In fact, you can combine that and you get 5/2 MA equals mg. Cancel out those m's. Just like before, we can get an expression for the acceleration. And if we can get an expression for the acceleration, we can use it to figure out other stuff about our system. Like we could put it back over here and figure out what the tension is, stuff like that. This is a pretty standard Newton's second law question. However, I've got a problem to share with you. So are we good so far? This is tough. This is hard stuff. Don't want to minimize it and you have homework, but I want to show you something before the bell rings. If I hang a weight on this side, like so. And let's just so I have something to argue about, 2m, m, and this is still 3m. First semester, when we did these problems, we would say that the tension here and the tension here were the same. Do you remember that first semester? That is not true anymore. That was only true when the pulleys didn't have inertia. Our pulleys have inertia now, which means the tensions have to be different if the pulley has inertia. The tensions have to be different if the pulley has inertia. You have to label this, say T2, and this one's T1. They are not the same. The reason is because there has to be a difference in tension or this won't turn. The only way this turns is if the net torque isn't zero. If the two tensions were the same, the net torque would be zero. I'm giving you an answer to a test question. You guys don't see it that way, I know. You think this is obvious. It is not obvious. So in this circuit, the moment your pulley has inertia, the tensions change because it takes an unbalanced torque to cause an acceleration. If the tensions were the same, that would be zero and that won't work. So suddenly you can't treat these tensions the same. They are different numbers, which means the tension upwards here is also T2. And the tension upwards here is also T1. Yes, sir?
There was no friction, then if the tensions were the same, an exponent would just still exist.
Yes. Like without the weights hanging off?
Yeah, like
Okay.
if there's the same tension on both sides.
Right, yeah, but that would preclude the weights not being there or them being the same weight.
Yeah.
Okay. Now, this is also true if my problem looks like this. If there's a I don't want to do that. It's not happening as fast as I want. I know I'm limited on time, but if you have this kind of arrangement, there, think that'll work? Okay. So this is an Atwood machine. We did this first semester. But in this case, if it's a heavy pulley, this tension would be different than this tension. Anytime the pulley is heavy, anytime, if there's a tension on either side of a pulley, the tensions will have to be different because it's the only way the pulley can turn. All right, there, we got that in your notes. Here's what I'd like to do.